Hi, my name is Bill Kinney and this is Quick Precalculus Review for Calculus Part 2. Also Part 2 of a unit on comparing and contrasting linear and exponential functions. Our main mathematical focus in this video is to review what we did in the last video where we focused on how to find a formula for a linear function when you are given an initial value and a rate of change or slope. And we're also going to focus on using the program that you see here, which is called Mathematica, to use a command called plot to make a plot in Mathematica. And the new thing in this video is we'll talk about how to dress up your plot to make it look nicer with some plotting options. Here was the example from the last video. The city of Austin, Texas grew from a population of about 790,000 in 2010 to a population of about 885,000 in 2013. Based only on this information, estimate the population of Austin in the year 2020. So let's do a quick review of what we did. We made an assumption, first of all, and whenever you're doing mathematical modeling, you have to make assumptions. And what we're assuming is pretty much the simplest thing you could assume. We're going to assume this is modeled well by a linear function. Is that correct? Not necessarily. We'd have to compare it with real-life data to see how well a linear function does, maybe based on past years. The general form for a linear function in this kind of situation is your quantity, in this case your population, is the initial value plus the rate of change times the time. I'm going pretty fast here with the math. I hope this is something that you've done before, but it's a quick review. In fact, we're going to be a little bit more specific than we were in the last video. I'm going to define what my variables mean. Let's be more specific. I'm going to let P represent the population of Austin. I should add that here. In thousands of people. I'm going to be specific there and say that this is in thousands of people. I didn't have to do that. I could have chosen people, but I chose thousands of people. I'm going to let T be my independent variable. P is my dependent variable, and T is my independent. That's going to be the time elapsed since 2010. We're not being specific about whether this is the beginning of 2010 or the middle of 2010. Let's not worry about that. Then P is a function of T, and this is standard notation to say that P is a function of T. F is the name of the function, and you say P equals F of T. It's going to be the initial value, 790, and you do type that as a 790 here if it is in thousands of people already, plus the slope or rate of change times the time elapsed T, in this case time since the year 2010. I hope you recall that the slope is rise over run. Change in P, change in population, delta P. The delta is the capital Greek letter delta, looks like a triangle there. It means the change in P divided by the change in T. You calculate differences to calculate those changes, and you get a rate of change, a slope of about 31.7. What are the units? The units for the dependent variable are thousands of people. The units for the independent variable are years. So the units for the ratio, the slope, the rate of change will be thousands of people per year, and here's the formula that you get. Here was the Mathematica code that I showed you last time to make a basic plot of this. Plot is the command, the function that is going to make a plot of this mathematical function. The input for a function in Mathematica, this program, needs to be inside square brackets, not parentheses. That is the standard in Mathematica. The first input here for this plotting function, plot, capital P, by the way, is important here, is the mathematical function you want to plot, 790 plus 31.7t. The second input, which is separated by a comma, is the window in the independent variable's direction. T varies between 0 and 10. This is called a list in Mathematica. It's got curly braces surrounding the inputs for the list. The first thing is the variable t, then you put a comma, and the second element of the list is the left endpoint of the interval. Put another comma, and then the third element of this list, the 10, is the right endpoint of the plotting interval. And here's our plot. I can enter that by doing putting my cursor on this line. Doesn't matter where you put it. You can see this cell, this line is one cell, and I can do a shift return to enter that and see the plot. Something new I'm going to do right now is I'm going to dress this plot up. Maybe I'd like to color it. Plot style is an example of a basic option within a plotting function. Notice I'm using another comma here. It's important to do capital P and a capital S. Then you put an arrow there by putting a minus sign, then a greater than sign, and watch, it'll magically turn into a better looking arrow as I type the word red. There we go. Capital R, this will make the graph red. I will shift return here to enter this, and we now see a red graph. But it's still kind of thin. I'd like it to be thicker. I can add another option to this. The word thick can go in here. next to red, separated by a comma, inside a list with these curly braces. And now I can enter this and it makes it thicker. I can make it even thicker by changing the thick command to a thickness command. And for example, if I put a 0.02 inside square brackets after the word thickness, that will make it pretty thick. I think maybe horizontally this thickness is perhaps 2% of the entire linear distance across here. I'm just guessing there. If I make this a 0.04, I think I double its thickness. And yes, that's pretty thick. What other kinds of options can I add? I can add labels for the axes, axes label, capital A, capital L, arrow, and inside a list I can put a T and a P inside quotes separated by commas, a comma. Enter that and you see the axes are labeled. Kind of small. I can format this by making these bigger, and I do get bigger output labels there for the T and the P. I can label the plot with plot label, and inside quotes I can label this as, say, the population of Austin in thousands in years after T years after 2010. Would be a good label there. In quotes there, now I can enter that and I can see that. And as you might guess, I can make this bigger too. Okay, so there's some basic plotting labels, dressing up that I can do with my plot to make it look nicer. I'll also inform you that you can do some other things with this. You can highlight the plot, you can save it, save the selection as, for example, a PDF file. Let's see, let's put it in here. Save that as a PDF or something else. I'll save it as a PDF. And then you can open that PDF file to see the graph. You can copy and paste it into a Word document, for example, or maybe a Google Docs. Well, I think we probably have to do a paste special here. Paste the picture or the PDF. And there we have it inside a Word document. I suppose a Google Doc would be very similar. Various kinds of things that you can do with this. Let's spend the rest of the last few minutes of the video considering a new example. Focused on the math of this. In example 2, we have a new car that was bought in the year 2013, and its price was $24,000. I could have written this as an actual $24,000, but by writing the word $24,000 there, I'm already emphasizing that I'm going to think of the units for the dependent variable as a price in thousands of dollars. In the year 2014, somebody assessed the value to be $21,000. I'm not saying whether they're right or not. I'm just saying that's what they assessed it. Based only on this information, let's approximate the value of the car when it is 5 years old. So once again, in our solution here, let's assume that, well, let's say V be the value of the car in thousands of dollars, and let T be the age of the car in years, or if I wanted to be more specific, years since 2013, since when it was new. The same kind of general principle here can help us come up with the formula. The general principle for the population model was the population, the quantity, was its initial value plus the rate of change of that population with respect to time. In this case, time is the independent variable. That rate of change gets multiplied times the time. That same principle will hold here. The value V is going to be a function of time, V equals f of t. It's going to be the initial value, $24,000, so I'll just type it as a 24, plus the rate of change, the slope, which are synonymous, times the time. What is the slope here? It would be change in V divided by change in t. The value of the car is going down. It is depreciating. That's what typically happens with cars. They go down in value as you drive them. They're not as valuable because they're old and because they're getting more worn out. Typically, cars go down in value a lot right off the bat, right when you drive it off the lot, but let's just pretend it's gone down by these $3,000 here. The slope, the rate of change in that case, over 1 year is -3. So I would write 24 plus the slope times t as 24 minus 3t. To save a little time here, let's do some copying and pasting to make a graph of this to try to help us answer the question. So I copy and paste that code. Let's replace the function with this. I'm going up till 5 years old, so I want t to go up to 5. Here it's a value instead of a population, and here we're looking at the value of the car for this plot label. Value of the car as a function of the age. There it is, 24 minus 3t, and we see that when t is 5, the value looks like it's 9,000. You should be able to, of course, check that by plugging t equals 5 into the formula. You get 24 minus 3 times 5. 24 minus 15 would be 9. $9,000 would be your estimate for the value of the car when it's 5 years old. Again, we're not addressing issues about whether that's accurate. We're just coming up with the basic linear model.